Newton and electricity. Between 1660 and 1675, Fabry and Boyle discovered that electrical actions are mutual. A few years later, in 1687, Isaac Newton included the principle of action and reaction as one of the pillars of the whole of physics. This is the third axiom or law of motion, which he included in his famous book, Mathematical Principles of Natural Philosophy, also known by the Latin name Principia. His third axiom, or third law of motion, was formulated as follows. To every action there is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal and directed to contrary parts. It is important to note that Newton believed this axiom should be valid for all known interactions: gravitational, electric, magnetic, elastic, contact forces, friction, collisions, etc. Moreover, to Newton this principle had both a qualitative meaning and a very precise quantitative aspect, namely, that to every action there is always a reaction of equal intensity. Moreover, they are aligned along the straight line connecting the two bodies, directed to corresponding parts. By action and reaction, Newton referred to the mutual forces between the two bodies, which are measured quantitatively by variations of the linear momentum of each body per unit time. What we call linear momentum, Newton called quantity of motion, and since it is proportional to the mass of the body multiplied by its velocity in relation to absolute space. What we call linear momentum, Newton called quantity of motion, since it is proportional to the mass of the body multiplied by its velocity in relation to absolute space. This fundamental work by Newton marks a new epoch in physics, an epoch in which science attained high degree of precision. In the Principia, Newton presented collisions and contact forces as examples of interactions that satisfy the principle of action and reaction. As regards action at a distance, he quoted the examples of gravitation and magnetism, discussing the latter in the following words. In attractions, I briefly demonstrate the thing after this manner. Suppose an obstacle is interposed to hinder the meeting of any two bodies, A, B, attracting one the other, then if either body, as A, is more attracted towards the other body, B, then that other body, B, is towards the first body, A. The obstacle will be more strongly urged by the pressure of the body A than by the pressure of the body B, and therefore will not remain in equilibrium. But the stronger pressure will prevail, and will make the system of the two bodies together with the obstacle to move directly towards the parts on which B lies, and in free spaces to go forwards with a motion continually accelerated, which is absurd and contrary to the first law. For by the first law, the system ought to continue in its state of rest, or of moving uniformly forwards in a right line, and therefore the bodies must equally press the obstacle, and be equally attracted one by the other. I made the experiment on the lodestone and iron. If these, placed apart in proper vessels, are made to float by one another in standing water, neither of them will propel the other, but, by being equally attracted, they will sustain each other's pressure and rest at last in an equilibrium. In Query 8 of his book Optics, Newton described experiments on electricity. Query 8. Do not all fixed bodies, when heated beyond a certain degree, emit light and shine? And is it not this emission performed by the vibrating motions of their parts? And do not all bodies which abound with terrestrial parts, and especially with sulphurous ones, emit light as often as those parts are sufficiently agitated? Whether that agitation be made by heat, or by friction, or percussion, or putrefaction, or by any vital motion, or any other cause? So also a globe of glass about 8 or 10 inches in diameter, being put into a frame where it may be swiftly turned round its axis, will in turning shine where it rubs against the palm of one's hand applied to it. And if at the same time a piece of white paper or white cloth, or the end of one's finger be held at the distance of about 1/4 of an inch or 1/2 an inch from the part of the glass where it is most in motion, the electric vapor, which is excited by the friction of the glass against the hand, will, by dashing against the white paper, cloth, or finger, be put into such an agitation as to emit light and make the white paper, cloth, or finger appear lucid like a glowworm, and in rushing out of the glass will sometimes push against the finger so as to be felt. And the same things have been found by rubbing a long and large cylinder or glass or amber with the paper held in one's hand and continuing the friction till the glass grew warm. Electricity is also mentioned in Query 31, where Newton emphasizes the mutual interactions at a distance between the bodies. Query 31. Have not the small particles of bodies certain powers, virtues, or forces by which they act at a distance, not only upon the rays of light for reflecting, refracting, and inflecting them, but also upon one another for producing a great part of phenomena of nature? For it's well known that bodies act one upon another by the attractions of gravity, magnetism, and electricity, and these instances shew the tenor and of course of nature, and make it not improbable but that there may be more attractive powers than these. For nature is very consonant and comfortable to herself. How these attractions may be performed I do not here consider. What I call attraction may be performed by impulse or by some other means unknown to me. I use that word here to signify only in general any force by which bodies tend towards one another, whatsoever be the cause. For we must learn from the phenomena of nature what bodies attract one another and what are the laws and properties of the attraction before we inquire the cause by which the attraction is performed. The attractions of gravity, magnetism, and electricity reach to very sensible distances, and so have been observed by vulgar eyes, and there may be others which reach to so small distances as hitherto escape observation, and perhaps electrical attraction may reach to such small distances even without being excited by friction. He also mentioned electrical attractions in the Principia. For instance, in Book 3, Proposition 7, Theorem 7, that there is a power of gravity pertaining to all bodies proportional to the several quantities of matter which they contain. Newton wrote, "Therefore the force of gravity towards any whole planet arises from and is compounded of the forces of gravity towards all its parts. Magnetic and electric attractions afford us examples of this. For all attractions towards the whole arises from the attractions towards the several parts." In the general scholium at the end of the book, he also mentioned electricity, emphasizing again the mutual interactions between bodies. And now we might add something concerning a certain most subtle spirit which pervades and lies hid in all gross bodies, by the force and action of which spirit the particles of bodies attract one another at near distances, and cohere, if contagious, and electric bodies operate to greater distances, as well repelling as attracting the neighboring corpuscles, and light is emitted, reflected, refracted, inflected, and heats bodies, and all sensations is excited, and the members of animal bodies move at the command of the will, namely, by the vibrations of this spirit, mutually propagated along the solid filaments of the nerves, from the outward organs of the sense to the brain, and from the brain into the muscles. But these are things that cannot be explained in a few words, nor are we furnished with that sufficiency of experiments which is required to an accurate determination and demonstration of the laws by which this electric and elastic spirit operates. These quotations show that in Newton's mind, electricity played a fundamental role in natural phenomena,